Hello, my name is Devika Nair, and my mentor's name is also Sana Bimani, and I'm actually doing the same topic. I'm doing this presentation in Fort Collins, Colorado, and again, I'm going to focus on the evidence surrounding dark matter. I'll also try and explain what dark matter is. I decided to research dark matter because I'm really interested in astronomy, specifically cosmology. I think it's really fun. First of all, what do we know about dark matter? Um, it's a hypothetical particle in the universe that's invisible to the eye and can't be detected using technology. It's extremely hard to detect because it only interacts with normal matter, protons and neutrons, that sort of stuff, via gravity. It's also theorized to be neutral in charge, and it accounts for a large percentage of the universe's total mass. It's classified as cold, which means it moves slower to its theorized hotter counterparts. It's also classified as stable, which means it's not supposed to decay easily. This gives dark matter the ability to have been around since the Big Bang, which is really important. And lastly, which I'm going to cover, uh, there's a lot of evidence to support it. Today, I'm going to discuss galaxy rotation curves, gravitational lensing, and the CMB. Galaxy rotational curves. They are plot graphs that track how fast stars and gases are moving around the center of the galaxy. The actual curve is different from the predicted curve, which is based on Kepler's third law, which states the further the planet from the star, the slower it will orbit the star. Scientists applied this logic to galaxies, but they were very wrong. Not very wrong, but they were they missed that dark matter would be there. Uh So that image on the right, it shows the predicted and actual galaxy rotation curve of the galaxy Messier 33. As you can see, the predicted curve decreases while the actual curve increases. This means that in reality, even with distance, stars and gas orbit the center of the galaxy with the same or even greater speed. Why would that happen? It's because there must be more matter that we can't see that's causing the stars and the gas to orbit the galaxy at a greater speed. So that's why dark matter fits this description. That's why galaxy rotation curves serve as evidence for dark matter. The next piece of evidence I will discuss is gravitational lensing. A gravitational lens is an object that refracts or bends light as it comes towards us due to its gravity. The image to the right shows an Einstein ring named after Albert Einstein and is an example of gravitational lensing. It's a rare case that happens when everything is perfectly aligned, including the viewer, the lens, and the light source. More commonly, light appears in fragments around the lens, is distorted, or the light appears repeatedly around the lens. There are three types of lensing: strong, weak, and microlensing, but since dark matter is mostly a weak lensing object, we will focus on weak lensing. With weak lensing, the lens is smaller than strong lensing, but not as small as microlensing. Examples include areas of dark matter and galaxies. Scientists observed that around what seemed to be empty space, there were distortions of background light sources like galaxies. This indicated that there was some invisible form of matter that was acting as a gravitational lens, bending light from distant galaxies. That's why gravitational lensing is another piece of evidence that supports dark matter, because we have observed dark matter act as a gravitational lens. The CMB and anisotropies, I think I'm saying that right. The last piece of evidence I will talk about is the CMB, which stands for the cosmic microwave background. It's the remnant left over from the Big Bang and the early universe. It's made of microwave photons, and it's very helpful in telling us information about the present day universe. And I mean, the early universe. And it serves kind of as a map. For example, it tells us that there were temperature fluctuations across the universe, or anisotropies, which led to fluctuations in density. More matter accumulated in certain areas of the universe, including and specifically dark matter. These differences in density across the universe eventually led to the formation of structures of galaxies and possibly galaxy clusters. This means that dark matter is responsible or likely responsible for creating the framework of the universe. Uh, the CMB and the angular power spectrum. The angular power spectrum is a graph that measures density fluctuations across different regions of the CMB that are more or less concentrated. It uses the angular scale, which measures the distance between different objects in the universe and helps determine how dense certain regions of the universe are. What do the peaks represent? The first peak, I think it represents the largest density fluctuations in the early universe. And I think it's based on acoustic oscillations or sound waves in, I think, quark gluon plasma. I'm not really sure what it is, but the second and third peak is more important. The second peak represents ordinary matter, and the third peak represents dark matter. The height of the third peak corresponds to the amount of dark matter in the universe. More dark matter equals a greater maximum and minimum density in certain regions, and therefore a higher peak. Overall, I enjoyed putting this presentation together, and I have a lot more to learn about dark matter, but I'm looking forward to doing so. Thanks for listening.
Devika, thank you so much for the presentation. Yeah, so any questions from the attendees or panelists for Devika? All right, so then I'll ask a question. So you mentioned how the cosmic microwave background radiation was a result of these early fluctuations, and that higher density corresponds to higher temperature and lower density to lower temperature. So can you help us understand how is it that we look around in the universe and we see these fluctuations? So is it uniform, or what does that tell us about the structure of the universe?
I think it wasn't uniform, that there was more matter in certain regions that eventually formed galaxies in certain areas, but empty space in others.
And do you know why certain areas were so much denser?
That's something I need to learn more about, but it's partly because certain types of matter would attract more matter in other areas, and areas with no matter would not attract any, but the areas with matter would keep on attracting more and more matter gravitationally, I think.
Yes, absolutely. Makes sense. And when you think about the cosmic microwave background radiation, do Do you know how it's observed?
Um, I think they have several detectors. Maybe I'm not sure if LIGO was one of them.
I think it's very closely related, but
Yeah,
that's a good thinking. Um, but also I think there are specialized detectors, and that's
yeah.
helped. Yeah. So Devika, what motivated you to do this project?
Um, I think I'm just a sophomore and I'm kind of interested in astronomy. And I
Mhm.
think the history of the universe is kind of cool. So yeah, I'm developing an interest in cosmology.
Makes sense. And what was the most challenging part? Oh, before I um, ask another question, I'm checking the audience. Uh, yeah. So, what was the most challenging part of this project for you?
Uh, I think the CMB is hard to understand. The angular power spectrum is also hard to understand because I'm not used. I don't. I'm not used to the concept of the angular scale. I still don't really know what
Yeah.
it is.
Yeah, it's a very challenging concept. So a huge shout out to you to even attempting to understand it as a sophomore. It's something that even graduate students struggle with. But got it. So these were areas where you felt like you had to challenge yourself quite a bit. Yeah, wonderful. And what's next? So what are you excited to do next?
Um. Uh. I'm excited to learn more about this cosmic microwave background. I think I need to learn more about the anisotropies and how that led to density fluctuations because yeah, I don't know the exact details. And also
Yeah,
I want to learn more about the particle candidates. I know a few.
wonderful. Well, Devika, thank you so much for that presentation. Great job today, and especially great job, dealing with these technology issues which keep cropping up. It happens. It happens to all of us, and it was wonderful to see you do so well and not get flustered. So, congratulations on that as well, and on this great project.
Thank you.
Wonderful. Yeah, thank you, Devika.